Hello everyone. In this video we're going to talk about the first part in section 3.4 of your book. This section is about PN junctions at open circuit, and we're going to cover diffusion current in PN junctions and the depletion region. So why are we covering PN junctions? PN junctions are diodes. So in this section you're going to learn more about the physics about how diode works. So just as a reminder, we have that a p-type semiconductor has majority carriers as holes, and the minority carriers in a p-type semiconductors are electrons. For an n-type semiconductor, the majority carriers are electrons and the minority carriers are holes. So what's a p-n junction? Here on the image on your, the first image that you see, you take a p-type semiconductor and an n-type semiconductor and put them together, and that's creating a p-n junction. And some interesting things happen once you have these two guys together. The first one is diffusion current. Diffusion current is related to majority carriers. So let's say on the p side we have a bunch of holes. You have here a bunch of holes. And the concentration of holes on a p semiconductor is way bigger than the concentration of holes on an n-type semiconductor. So having a higher concentration on the p side and a lower concentration on the n side, what the holes are going to try to do is to diffuse into the other side. And this is all related to diffusion current, and we talked about that on the previous video. So these holes are diffusing from left to right, from the higher concentration to the lower concentration, creating a current going from left to right. Then a similar thing is going to happen with electrons. Let's see. We have a higher concentration of majority carrier electrons on the n side of the p-n junction, and these electrons are going to diffuse into the p-type or the p side, because the concentration of electrons is higher on the n side than it is on the p side. And electrons are going to be flowing from n to p, but we know that by convention the current goes opposite to the flow of electrons, so we're going to have a current going from left to right. If we add up these two currents, we're going to end up with a total current, a total diffusion current ID, going from left to right. So that's important. So what's the depletion region? First, let's remember what happens when, let's say, a hole right here is here and it is diffusing to the other side, we're saying. And the n side is doped with phosphorus. Let's look at the image here on the right. Let's remember this is a silicon lattice. Let's remove the silicon and add a phosphorus. This phosphorus has, and we know, 5 valence electrons, so after all the covalent bonds are formed, we still have an extra electron here. So let's say this hole right here is traveling from the p to the n side. So I'm going to draw it right here. This hole travels from the p going into the n side, and it's going to want to recombine with this electron right here. After that recombination happens, this phosphorus is left behind with a bound charge, a positive bound charge. And remember, bound charges don't move. So close to the junction, when all these things are happening, we're going to be accumulating a bunch of positive bound charges on the n side. So this charges are going to be accumulating there on the n side. Now let's see what happens on the p side. So let's see. Now we have electrons here. We have electrons here. These electrons are diffusing, we said, into the p side. So let's see what happens on the p side. On the p side, we are doping it with boron, which is a group 3. It has 3 valence electrons. So after the covalent bonds are formed, we still have a hole that's there due to the boron. So if you have these electrons from the N side going into the P side, this electron is going to try to recombine with this hole. So after that recombination happens, boron ends up with a negative bound charge. So you're going to be forming negative bound charges here on the P side. And then some interesting things happen after we have these bound charges there. So we're gonna forget about the image on the right now. So here on the left, remember, or as you can see, we have a positive charge on one side and a negative side charge on the other side. This creates an electric field going from positive to negative. We have an electric field right here. So that electric field, if you can see, is going to stop. Let's say we have, let's do it in red, we have some majority carrier holes here that we're diffusing into the other side, but now they're facing a barrier, they're facing an electric field that's gonna prevent them to keep flowing into that side. So after these band charges are created there, we create what is called a depletion region, and that depletion region acts as a barrier for more majority carriers. The same thing will happen with electrons to flow from one side to the other. So that's one thing. These electrons are going to face, these majority carriers electrons are going to face this barrier, and they're not going to move there. So that's one thing that happens after the depletion region is formed. Another thing that we can see from here is that since we are having a positive on one side, negative on another, we're basically creating a voltage. This voltage is called built-in voltage, something like this, and we can see it here on our formulas on the right. This built-in voltage right here, is related to thermal voltage and the concentration of acceptors and donors. So obviously after this depletion region is created, you have an electric field, and you can think, okay, now we have an electric field, so a drift current is going to be created. And that's what we're going to talk about on the next video.